Hi guys, before we move to the transistor theory, I just wanted to say a word or two about the DIY electronic synthesizer enthusiast. There's basically 4 ways you can go about your craft. One is to buy complete kits, and then all you have to do is follow the instructions and assemble them. A slightly harder, if more rewarding approach is to simply buy a circuit board and design your own panels, do all the physical mounting of your module, and in that case you have a slight bit more work to mount the pots, the front panel, and connect your module to it. More difficult mechanism would be to get your own board. In other words, you're starting with nothing more than a circuit and you're designing using some kind of wiring mechanism, either Vero strip or etching a board or having a board made for you. But you're going from a simple schematic, and of course this is more difficult and calls for more ability on the part of the DIYer and experimenter. And then finally we come to the last category, where you're actually designing your own circuits. And I don't know which level you want and which level you are going to be satisfied with. But when I'm teaching a university course to my students, we are on the theory level. We want to understand more than simply following a circuit diagram to assemble. And so that is the topic of tonight's video. We are going to be giving you the theory behind the transistor designs. And when I come to give you a new circuits to build, I have to decide at what level I'm going to pitch this. Am I merely going to draw the schematic and throw it your way and leave it up to you to build? Am I going to get some boards prepared for my unique creations and let you order the board? Am I going to go further and have a part stock and put them into little Ziploc bags and have a front panel etched and sell you the whole caboodle so that all you have to do is to build it? Guys, let me know what you want in the comments below. It is obviously going to be a bit boring and mathematical with what comes in a moment or two. But this is for those guys who actually want to learn electronics. So guys, what do you want? We can give you your favorite poison. Let us know in the comments below. And now we will go to the theory. We begin by looking at the bias requirements for the transistor. The first one we would look at is the simple base bias. As you can see, the resistor on the base is connected to the positive voltage, and therefore the transistor is forward biased. Although this is very simple, it's quite undesirable to really use this mechanism to bias the transistor. What we have to do is we have to insert a resistor in the emitter, and this is referred to as emitter-stabilized bias. And one of the big advantages of this is that it stops the thermal runaway in the transistor. And as you can see, It does this by reducing the bias as the current through the transistor increases. A better configuration that will ensure that the transistor operation is pretty independent of the beta or HFE parameter is the voltage divider bias on the bottom right. As you can see, a voltage divider is applied at the base, and because the values of the resistors can be chosen to make this a stiff voltage divider, the voltage presented at the base is pretty much independent of the actual transistor that you stick in there. Good design practice in the art of electronics is to try and make the circuit as independent of the transistor parameters as possible, because the transistor parameters vary widely even for a similar transistor, one with the same number. The last bias configuration that we look at is the collector feedback bias on the bottom left, where the bias current actually goes through the collector resistor RC. These are the most common bias configurations, and we will now examine them in more detail. We will start with the emitter-stabilized bias. For all of these circuits, we assume that the voltage between the base and emitter, referred to as VBE, is 0.7. Some books take it to be 0.6, but it varies slightly in reality, in practice, between 0.6 and 0.74, or some small variation. So we have to have a theoretical model for analyzing these circuits that brings us into the real world, where we actually operate with real components. So it's perfectly legitimate to take it to be 0.7 volts, because it's not going to vary more than 0.1 of a volt in either direction. Next, we realize that based on an observation of the circuit on the left, the emitter current is going to be the sum of the base and collector currents. This is just simple Kirchhoff's current law. We also see, because of the current amplification characteristic of the bipolar junction transistor, that the collector current is going to be beta times the base current. Beta is normally shown as HFE on the parameter and data sheets that you get for the transistors. It is the current gain in the common emitter configuration, which is what we are considering at this point in time. We need some idea of what voltages to expect at the collector, base, and emitter. We can write expressions for those voltages. At the collector, we have the supply voltage minus the voltage drop across resistor RC, which is simply the current multiplied by the resistance according to Ohm's law. For VB, we have the voltage, the supply voltage, minus the voltage across RB, which is simply the current multiplied by the resistance according to Ohm's law. And for the emitter, we have the sum of the two currents. IC and IB, which leads us to beta plus 1 IB RB. We can write the IE now in terms of that, so that we get IB beta plus 1 as the emitter current. Now we turn our attention to Kirchhoff's voltage law to divide the supply voltage across the components, coming down with, first of all, the voltage across the RB, which is IBRB, then the voltage of 0.7 between the base and emitter connection of the transistor, and finally the voltage across the emitter resistor, which is just IERE. We now expand that by substituting the beta plus 1 IB for the IE, as shown there. Finally, we bring the VBE constant voltage over onto the other side of the expression, so that we have voltage on the left, and on the right side we collect up the terms. It's just simple algebra, and we divide by the expression within the brackets here, so that we may make IB the subject, and we now have all the equations necessary to solve for voltages and currents in the biasing of transistors using this mechanism. We now turn ourselves over to the voltage divider bias, which is by far superior in that it makes the Q point of the transistor more immune to changes in the parameter beta or HFE. The first part there with the currents for the emitter, collector, and so are just copies of what we had in the other case. The equations change where you see the green part for the voltage at the base. The others are identical to what we had in the last example. What we're doing here is providing an accurate equation to work with to find the current and IB at the base. So we replace the voltage divider network of R1 and R2 on the left with the Thevenin equivalent circuit. And when we do that, we have the Thevenin voltage expression there and the Thevenin resistance expression there, and we merely substitute that as shown in this base circuit here. So that base circuit there in green accounts for our analysis. So we write this in terms of VTH. As you can see, it is a Kirchhoff's voltage law or loop around this. And then we make IB the subject of the expression as we did in the last example. We now take a look at the collector feedback bias circuit, and we see that the same transistor behavior applies. What we have there on the right side applies to all of them. So now what we are going to do now is look on the voltages, and we see that the only one that's really different here is VB. Okay? And we notice that in this particular configuration, the current is exactly the same through the resistor RE and RC, because as we can see, the base current recombines, so the same current is flowing through here as is flowing through here. And we have just put it all small there so that we can now develop the equations that we need. So that's a pretty much standard equation, and that gives us KVL there, then over here, then down here. So we end up with 4 terms of the expression all added together. And then we substitute for the IE. Substitute for the IE right here. That's what we've done in that one. Then we gather up, and once again we bring the brackets underneath so that we have IB as a subject. Pretty much standard algebra. Now we look at the AC equivalent model, and the first one we're going to look at is the common emitter. As you can see here, we have an unbypassed emitter resistor. We introduce the idea of coupling capacitors. And the purpose of coupling capacitors is to pass the AC but block the DC so that our bias Q point is maintained. So we take the output from the collector, as you can see, and we expect at the collector a larger inverted copy of the smaller input signal. The common emitter configuration has 180 degrees phase shift between the input and the output, and we leave that one to you to figure it out. Why? But we want to speak about the gain. Gain is always the output over the input, and it's just a number. It doesn't have any units. You just multiply the input by that to get the output. And of course, we have 2 things we are considering: the current gain or the voltage gain. So the current gain would be the gain in current. These BJT transistors are primarily current operated devices, but we can get a considerable voltage gain out of them by the proper choice of supply voltage and the collector resistor. We are also concerned with trying to understand what are the input and output impedances of the situation, because that is going to be important when we try to use this transistor amplifier in some kind of device beyond itself. We have introduced there a capacitor that bypasses the emitter, and so it is referred to as a bypass capacitor. The only difference between the bypass capacitor and the coupling capacitor is the job that it's doing in the circuit. But basically, the capacitor is always passing the AC and blocking the DC. So the purpose of bypassing the emitter is so that our emitter will be grounded emitter, also called common emitter, for the AC signals we're trying to amplify, and yet we will still be able to maintain the emitter at the proper DC voltage established by our emitter resistor. So, the common emitter configuration, in a nutshell, accepts the input into the base. The emitter is common or grounded to all two signals, and it gets the output from the collector. Most popular of all the transistor configurations. We now move to the common base circuit. One would expect that the biasing is the same. Notice we have the same biasing. It's still a voltage divider bias with emitter stabilization resistor. But now we have the base grounded with a capacitor, so that the base is essentially ground for AC signals. The AC signals are the actual signals that we're trying to amplify. And we put our signal into the emitter and take it out of the collector circuit as shown. So that kind of configuration identifies the circuit as a common base circuit. We use similar coupling and bypass capacitors in the same role that we did before. And we stress that the job of the capacitor is always to pass AC and block DC. So it puts the base at ground potential for AC signals. Now, if we look at this circuit, we realize that this circuit has to have a current gain of less than 1. Can you see that? Why would the current gain be less than 1? Well, the emitter actually has more current flowing through it. The emitter resistor has more current flowing through it, and the collector resistor has less current flowing through it. So there's no current gain in the common base circuit. We come now to the common collector circuit, also referred to as an emitter follower. And in this circuit, the collector is grounded for AC purposes. So we have at the top a bypass capacitor going across the collector resistor so that the AC circuit, the collector, is grounded. It's important to realize that any power supply is going to have a very low impedance to ground. Typically, power supplies have capacitors across them at their output to ensure that as far as AC signals are concerned, the DC power supply is a short circuit to ground. We can use a larger resistor at the emitter
and connect the collector directly to the positive voltage, and this is very frequently done. Obviously, the common collector circuit must have a voltage gain of less than 1. Can you see why? Well, the voltage at the base is always going to be higher than the voltage at the emitter. There's no way to get around that. So the emitter follower has a tremendous current gain at the expense of no voltage gain. And the emitter follower is often used to convert to a high current when we're trying to drive low impedances like speakers. A speaker is an actual current-driven device. Takes current to move that voice coil back and forth. So the emitter follower is the perfect arrangement for that. So that's about it for today, and we'll see you in the next video.